Welcome everyone. In this video we are going to prove a very widely used vector identity, that is, well, this. So you have a double cross product, let's say, double curl I mean, and this is equal to, it turns out, as we will see, well, equal to this. So we want to prove this. How do we do the proof? Well, there are multiple ways. The long way would be to write all the components explicitly and see that both sides give the same components, so they're equal. Or you can use the index notation. You can use the Levi-Civita symbol and the Kronecker delta to simplify the situation, which I will do. I understand that if you have never come across index notation before, this video will be completely nonsense to you. You will not understand anything, and I apologize for that. But I'm sure if you do a quick search on the topic, you will be able to understand this video. So we're using index notation, and if you look around and still can't figure out how this works, please let me know in the comment section. I will do a specific video on this topic. So we are using index notation, and you can, another key thing like Levi-Civita, you can search that as well to understand what we're doing today. But let's get started then. We will first consider the ith component of the left side. Okay? This will be equal to epsilon ijk, then the jth component of the first one, and by the way, this is the first one. Okay? So the jth component of that, I'll denote with like that, del j, and then the kth component of this. Let's write that out. So the kth component of this. Okay, moving on. Now we have epsilon ijk, del j, and then we want to now expand this guy using epsilon ijk and similar stuff. So it's going to be epsilon. Well, we have k, but the other two indices, they will be different. So it's going to be klm. Now we have the lth component of the first one, which is del l, and then the mth component of the second one, fm. Okay? Here we will use a very important relation between Levi-Civita and Kronecker delta. And I will write it with blue here maybe. So epsilon ijk, epsilon klm turns out equals Kronecker well, I'll try to recite it. il, I don't want to refer to any of my notes, so I times l, and then jm minus Kronecker delta, let's see, im, and then jl, I believe. I'll check my work just a second. And that is correct. Okay, so this is the relation that we will use. This is very important, and I can make a proof of this in a future video if you want. So leave that in the comment section if you want to see that. So I'm now substituting that, and I will just multiply so I will write the two terms separately, right? That's what I mean. So we will have the first term, and then we have del j, del l, fm, minus the second term, and now del j, del l, fm, right? And so this is going to be, now here comes the magic, let's say. You know, the Kronecker delta is equal to 0 if the two indices are different, and if it is equal to 1 when they are the same. So when we do the sum here, for this to not be 0, all the i's should be the same with the l's. So we can, instead of I, we can just write L. I mean, instead of L, we can just write I, or instead of I, we can just write L. I'll just write I for the L's. So here I'll just write del I. And we don't need this anymore because it's just 1 when I is equal to L, and it's 0 when I is not equal to L. And similarly here, we can replace all the M's with J's. And we could do the opposite. We could replace all the J's with M's. I just prefer to work with I, J's, and K's. Okay. So I will replace this M then with a J. So we have, this is staying. So we have del J, Fj, minus, again we're playing the same game. I will replace the M with an I. So Fi. And then if you look at here, instead of L, I will write J. So del J, del J. Cool? Now, you can notice that we have a repeated indices here. And that happens when we're doing a inner product, when we're doing a dot product. So we have del I, and this is nothing but the divergence of f minus, again we have the same business here. This is that, and then we have fi, right? Moving on, so we keep this one, let's say, and then I'll just write something else. And of course, this is, when we do this is in fact the same as the Laplacian. And you could see that well, because if you multiply them, you have d by dx, you multiply with d by dx. Well, it's a funny way of saying multiplying, I guess, but you have another d by dx, so now it becomes a squared derivative operator. So these two are equivalent. And then we have fi. And look at this. This is true for the ith component. And you could replace the I with j and with k. You could in fact do this for any component. So we have in fact proven that this identity that we start out with is correct. Because we showed that any component of the left side equals any component of the right side. No, what I mean is the ith component of the left side is equal to the ith component of the right side. So the two sides are equal to each other. Hence, this is a vector identity. I want to prove this because, in fact, in the next video, I will use this while dealing with electromagnetic waves. Specifically, I will use this vector identity in one of the lines of proof to show that the Maxwell equations in vacuum describe electromagnetic waves. Okay, so look out for that. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.